we talked about how A star was admissible. The solution was guaranteed to be optimal. But I didn't talk about why A star expands the fewest nodes of any other algorithm. And basically, it's this thing that I have been saying all morning, or all afternoon, all class, that A star is expanding all nodes with f less than f opt. And why does it have to do that? Why does it have to do that? Why does A star have to expand every node that's f values less than f?
That it is finding all the possible paths without going past what it should have been. Or it's all the nodes in between. Or
Nathan.
All those nodes that each could be perfect, in which case that's where the goal is.
Yeah, absolutely. It's that opportunity not taken that will haunt you for the rest of your execution. Yeah, exactly. So yeah, don't pass it up. Seize the moment. Seize the opportunity. Expand that node if the f is low, because it might be optimal. Otherwise, you'll never know. And A star expands all those nodes. Now, how can I guarantee that that's going to happen? Well, by this argument, this two-step argument. Here's a cool property, and this is the real reason I'm showing this proof, is so I can tell you about this cool property. Let's say I'm doing a search. God, I love search. And let's say we're expanding some nodes. Let's say f here, well, let's see, g equals 1, h equals 3, so therefore f equals 4. And then I have some child node here, and g is now 2, of course. And what if my h is now 1? So my f is going to be 3. Could that possibly be correct? Could that h value possibly be 1? Let's say my heuristic is guaranteed to be admissible. My heuristic, Joe, not my algorithm, my heuristic function is guaranteed to have the property of admissibility, which was that it's exactly optimistic. It wakes up on the right side of bed every single frickin' morning. Okay, so 1, could that be right? Let me further embellish the scene by telling you about this node, the sibling node here. G equals 2, obviously. Let's say h here equals 4. Okay? So the f of this node over here is 6. Can this h value of this node possibly be 1? What do we know about that node? You've just been talking a lot. Is there anyone who hadn't been talking much? Priya, can you tell me anything about, like, this is f equals 4, this is f equals 6. I'm about to write f equals 3 there, and I'm not happy about it. Because remember, with A star, right, we're going to have to expand all the nodes whose f value is less than f star. And so we want to pump up our f values as much as possible. I'm about to write 3 here. And that's making me mad. Why is that making me mad? I know with mathematical precision that there is a solution going through this node that costs at least 4. And that's the best I can do. I know with mathematical certainty, because H is admissible, non-overestimating, it's optimistic, that there's a solution to the goal through here with cost. If there is a solution through here, it's going to cost at least 6. So how could it be that the best bound, less lower bound I could have here is 3? Because here it was 4, and this is 6. So this has to be at least 4. Right? Because in order to get to a goal from here, I've got to go through one of the kids. Right? So that I know that h is too low. I know that h can be at least 2. I know it, because here it was 3, and it's admissible. It's optimistic. And I only incurred a cost of 1, so my cost to go can go down by at most 1. So this really ought to be 2 here. And this really ought to be 4. That could still be too low, but boy, it's a lot better than 3. So you can take H, an admissible H, along any path and do what's called path max, which means you take the max along the path. And so if you've already seen 4 here, and then you get 3 here, you know it can be a 4. You just know it. It's going to be 4 or greater for all the kids of this node. Now here it's already 6, so that's great. So it's called path max. So we know you can always do that. Path max is always legit. Right? Jeff, am I convincing you? Okay, you looked a little skeptical there for a moment. Okay, so for an admissible H, the F values along any path are now going to be non-decreasing. F is only going to go up as we go down a path. That is a cool property. What that means is that if I want to make sure to visit every node with F less than F star, I just expand nodes. I expand the minimum F node, and if the min F node is F star, I know that there don't exist any nodes anywhere in the search space with F less than F star. Because my entire open list, if F values only go up, then if this is the F star minus 2 layer, I keep expanding nodes, and maybe all these nodes have an F equals F star minus 1, and then here's the F star layer. Because F's, here's the root of the tree, right? I'm expanding out. Sorry, I didn't draw the trumpet this time. I know that if I keep going along any path from here, the F is just going to go up. So it's not like there are low F nodes hiding somewhere else in the tree. I know I've got them because my entire open list costs at least F star. And now when I expand that goal, I know it's optimal. So A star is expanding all the nodes it has to expand, and if you do the tie breaking right, no more. So it's optimally efficient. So anyway, A star is a fabulous algorithm. Good luck implementing it. It's just the best first on H. It's not the break yet. When we get the break, I've got harsh words. Okay, heuristic functions. We did that. Okay, now